So in this final lecture on blast and pressure from a nuclear weapon, we're going to be looking at effects on materials and structures. Now there's two types of pressures, as we've learned previously. There is overpressure and then there's dynamic pressure. You know, the shock wave, the front of the shock wave itself, and then the moving air behind the shock wave. Now these two things interact very differently with materials, structures, and objects. Now in the case of overpressure, the most damage that overpressure will do to a structure is based upon a moving pressure differential throughout the structure. Now, if we look right here at this diagram and we start here, the pressure wave is about to be incident. Nothing's happened quite yet. As soon as it touches, impacts the front of the house, we now have a high pressure zone on one wall. Okay, the blast wave though is going to continue to move, and it's basically going to bend itself around the house. Now when this happens, I'm not an expert in the aerodynamics of the vortices forming and how this pressure actually curls around the sides of something like a flat wall. But the long and the short of it is, as the blast wave, as that pressure front moves past the house, it starts to create not only pressure on the front, but then additional pressure on the sides of the house. Until it finally, when it passes the house entirely, and there is a zone of ambient pressure that is near, in this case, like say the back wall of the house. Now this is a problem because we have extremely high pressure of the blast wave, and we have ambient temperature or pressures in the house and behind the house. And we know that high pressure wants to equalize with low pressure. So by trying to do this, that blast wave is exerting a force inward on that lower pressure region. In effect, what it's doing is it's squeezing the structure, the house in this case. And that's where the majority of the damage comes from. And this is something called diffraction loading, because it's diffracting or basically bending itself around the house. And again, that pressure differential is what stresses things like the building supports, the walls themselves, the roofs, everything that can be broken or ripped down in a house. This thing is going to do its very best to squeeze it until that happens. Now the second kind of loading is called drag loading, and this is not from the overpressure from the blast front, but this is caused by the dynamic pressure following along behind it. Now in this particular example, you see that it's kind of like an open type structure, similar to what I think that actually reminds me of like a fire watch tower in a national forest, but it's truss and girder construction similar to something like a bridge or a radio tower or some of the bigger above ground power line structures. These things aren't really going to have that differential effect. As the blast wave goes through there, it's the same pressure just moving all the way through, and we never see that diffraction effect or that squeezing effect. So the blast front passes right through, but what happens is all of that wind, that moving air behind the blast wave, will then come along and just start to push everywhere on the structure, doing its level best to knock it down. And this is called drag loading because literally the wind, the air is dragging on the components of these structures and exerting pressure on them all over. And as you can imagine, if you provide an excessive amount, and we see this with things like, hurricanes, right? So sustained gusts of wind that don't necessarily, there's not necessarily a pressure differential, but just the force of the wind, the velocity of the air molecules impacting on things is more than enough to rip stuff out of the ground, to knock things over. And this is all that dynamic pressure acting. So we have two different ways that the pressure can interact. We can have the diffraction loading, which basically means that the overpressure is going to squeeze something due to a pressure differential that develops, or the wind that is coming behind the pressure wave, the face of the pressure wave, is going to impart just force on all parts of other structures that aren't affected by that differential pressure. So in this case, and this is the way that all of the damage from a blast wave or shock wave occurs. Now, what affects how different things respond to these two different applications of force and pressure? Well, if you have something that's big and heavy, a lot of inertia, doesn't really want to move, it's going to fare a lot better than something that's of a much lighter construction, where that where the drag force can really stress and overcome things like joints of building materials. So if you have something that's big and heavy and massive, it's probably not going to go anywhere. Now, it still will suffer if it's an enclosed space. It still will suffer from diffraction loading, where we have those two different pressure zones. And as I mentioned before, once that gets in there, once you have the pressure breaching into the structure, it's just going to squeeze and squeeze and squeeze until finally, it's going to equalize somehow, and it'll equalize with the outside pressure. So now that diffraction loading causes an area of high pressure within the building as it's trying to equalize. But then after everything is passed and now there's lower pressure outside, you could very possibly get forceful ejection of everything inside the house or the building. But a concrete structure, it's not going to fail. The walls aren't going to collapse in. They're not going to crush in. You're not going to see the ceiling collapse. None of this is going to happen because it has the mass and the strength to withstand something like that. Similarly, for drag loading, again, if you have something that's really hard to push over, the more massive it is, the more difficult it would be to push. And so that, again, we have these heavy inertial structures and objects much better capable of resisting the effects of both portions of the incident blast wave. Now, when we look at design, some structures are designed to withstand very high pressure loads, mostly for winds, especially places that are built near where tornadoes are prevalent, or where hurricanes occur rather frequently. There are some, of course, within the United States that were built specifically to withstand a nuclear strike somewhere in their vicinity. Mostly military structures, command and control, continuance of the government, bunkers, that sort of thing. And these were built to be able to handle both that overpressure and a dynamic pressure without suffering any harm. And this has to do with, openings that are covered with materials to not allow that overpressure to work its way into the building to further cause damage, and to avoid being, to avoid being squeezed or pushed over. These buildings that were specifically designed against nuclear strikes, you can basically push at them with, the equivalent of 10% of their mass or their weight, the force that their mass is exerting by gravity. 10% of that can be loaded onto them, and they'll be fine. So really beefy things. And then finally, another factor is the ductility or the flexibility of whatever it is you're looking at, mostly materials that structures are built out of. Now, ductility, it's basically a measure of how elastic a material is, so that it can bend without breaking, but not permanently deforming either. Think of it as taking a piece of thin plastic, and you can flex it quite extremely, but then when you let go, it goes back to its initial shape. So that's kind of the property that is represented by ductility. So Things like steel, some woods that have some give to them, if you will, some flex without sustaining damage. These are good for building materials to withstand pressure loading. Bad stuff is, unfortunately, very we'll call it hard or brittle materials that over a certain amount of pressure loading, they don't do anything until you hit a critical limit, and then they fracture. Hopefully this makes intuitive sense, right? So if something can give without breaking, it probably can withstand more pressure or more force against it than something that just has a line in the sand where if you apply more enough force past that point, it'll simply fail. So how do we categorize damage? Well, there's 3 different categories that are in ENW, and these are severe, moderate, and light. And these are and you can read this for yourself, but these are how they categorize them. Basically, severe damage means that you can't use the thing again, and if it's a structure or building, it means it's probably going to collapse. If it's like a tower, like a water tower or radio tower, it's getting pushed over. It's going to be pretty much a complete loss. Moderate damage is something that can be fixed afterwards. So it did have some failures in portions of it. Perhaps for something like a building, a part of the roof ripped off, or I don't know, like one wall has a crack running all the way down through something like masonry. It's not catastrophic. It can be repaired. But it is going to be noticeable damage. And then we finally have light damage. This is stuff like broken windows, missing roof shingles, rather inconsequential and very readily remedied. So these categories are here, and we have 2 different tables, 5.19a and 5.19b. From your text, and these show the different types of damage for various structures that are affected by different types of pressure loading. So for example, structural types 1 through 5 are affected primarily by diffraction loading, and it tells you what kind of buildings they are. For example, number 1 is a multi-story reinforced concrete building, concrete walls, blast resistant design, kind of like something meant to withstand a nuclear bomb. So severe damage to that would mean the walls are shattered, the frame is distorted and twisted. It's basically a complete write-off. Moderate means that some walls may have holes in them. You could have the frame distorted somewhat, although generally speaking, that to distort a frame would imply that, if you think about it, that the walls had enough pressure put on them so that they pushed inward or bowed outward. I guess technically that can be fixed, but is somewhat involved. Doors blown in, extensive spalling of concrete, and that just means that chips and chunks taken out. That's what spalling is. And then light damage is basically just a little bit of cracking, nothing major, no distortion of the shape of the building. Now, compare this to, I'll go all the way down to number 5, which is basically a house. Severe damage to a house, wall framing cracked, roof severely damaged, interior partitions blown down. Just what you would think of when you see a house that's been directly hit by a tornado. Roofs lifted off, walls can be standing or not standing, walls can be blown down. Nothing inside is going to be structurally sound. All of the inner partition walls for different rooms, that again, as that pressure differential becomes equalized and then wants to become equalized again, it just batters things down as it tries to reach that equilibrium. Moderate damage, the wall framing is cracked, roof is still severely damaged. Oh no, sorry, that was moderate damage. Severe damage is it collapses. Sorry, I lost my place when I was looking at that. Severe damage, the whole building just collapses. Moderate damage is things like interior walls being blown down, part of the roof being missing, the framework of the house being damaged itself and requiring extensive repairs. And then light damage is the same as it is in the building above. You lost some windows, maybe a door, and that's about it. Now, that was for diffraction loading. If we look at the next structural types, they are primarily affected by drag loading. So this is being pushed on by the wind. So we have light steel frame building, number 6. Think of something like a pole barn. If you're familiar with what that is, it's basically just a frame with some metal sheet work attached to it. Single story with up to a 5-ton crane capacity, low strength walls which fail quickly. Yeah, so this is either a pole barn, or think about like those metal, the inexpensive metal sheds that you can get from, I don't know, a place like Sears or something. It's basically a thin metal framework with thin metal panels screwed to it. There isn't much to that structure at all, and in fact, walls are very easily dented by, running into it with your mower or the neighbor's kid or something like that. So this would be typical of one of these, of this category 6 structure. And just by knowing how easily something like that is damaged inadvertently, by, contact, imagine now the pressure, high pressure coming from a nuclear detonation. These things, if they're within any kind of reasonable distance, they just get destroyed. And so severe is basically the same as it is for a house. It just gets wrecked. Moderate means that you might have some twisting, some deformation. Maybe it's taken the roof line and pushed it back a bit, so the whole thing is like a parallelogram now. That kind of thing that would require some extensive repairs. And then light damage, it says windows and doors blown in. You could have some separation of the skin from the support beams, so that they flap a bit but weren't actually ripped off. That would also be something that I would consider light damage. And then it goes on, pages and pages of these things, descriptions of what building or structure that they're talking about, and then what they consider to be severe, moderate, or light damage. Okay, so great. How do we determine whether or not these things are going to happen, and how do we know at what distance or what overpressure is going to cause it? Well, unlike the more I would say precise method of determining peak overpressures and peak dynamic pressures that we looked at in the last lesson, this one is just basically kind of this chart, and this chart has a very specific purpose. It's based off of weapon output, structure type, and distance from structure. So it kind of generalizes and lumps in all of those different categories or parameters that we looked at for determining overpressure and dynamic pressure. And it just kind of averages them out, I suppose, over for a weapon. Atmospheric, I think this is, for a weapon detonation. So we have, as you can see, we have 3 axes, basically. So we have this axis right here, which is distance from ground zero. And then we have 2 axes here. The one on the outside, where this set of numbers are, this is moderate damage for a particular yield weapon in kilotons. And the inner one is severe damage for a weapon yield in kilotons. So the first thing we're going to look at is this. So these cones represent those different types of structures that I showed you on the previous slide. So if we want to know what kind of damage is going to occur, or at what distance our moderate and severe damage is going to occur, we're basically drawing lines into these cones that represent the building types. So in let's take, for example, what's on here, which is a 1 megaton weapon, or 1,000 kilotons. So if we draw a line from where it's marked on the moderate yield, and we go ahead and trace it all the way out to the vertex of this little cone, we find out that moderate damage will occur 32,000 feet approximately. So this is 1,000, 10,000, 20,000, 30,000. We'll call that 32,000 feet. Any closer than 32,000 feet, it will definitely suffer moderate damage. Anything farther away, probably not. If we take that same approach with the severe damage line, and again, at the 1 megaton, and also trace it into the vertex of the cone, we find out that, well, severe damage actually happens at about 30,000 feet from ground zero. So everything up to 30,000 feet is severe damage, and then you have moderate damage from 30,000 to 32,000, and then it just falls off after that. But it's a house. I mean, it's a house. I didn't expect that a normal two-story regular construction or single-story, two-story wooden frame construction house would be able to survive the overpressure from a 1 megaton blast if it was anywhere near it. So let's look at something really durable. So let's take a look at that same weapon, but on that severely hardened industrial multi-story building, which makes up category number 1. So do the same thing, and what we find out is, again, that difference, that distance for moderate damage while avoiding severe damage is extremely small. But the distance at which these occur is much closer than it would be for a building of type number 5. In fact, we see that 7,000, just shy of 7,000 is going to be our severe damage, and just over 7,000 is going to be our moderate damage. So again, a very small window over which to differentiate what you think should happen. Now again, this is all just estimation. This takes in and kind of smooths out a lot of the intricacies of doing the calculations to determine exactly what will happen in order to provide convenience, if you will. So you can just look this chart up and draw some lines based on weapon yield, and you could look to see the approximate distances where you should expect these two types of damage. So that's at, just shy of 7,000 feet is when even that nuclear bunker constructed thing fails catastrophically. But it's an order of magnitude closer to a 1 megaton detonation than our wood frame constructed dwelling or house. Now, drag sensitive targets that are above and beyond what we just looked at, and these are things like vehicles. Again, there is a complete list of what these things are by number in the textbook. This is just doing the same thing, except there's not a difference in yield. There's just a single yield. And what we're seeing is that instead of having these cones with two different lines that we're running our intercepts through, we have numbers that have then further sub-designations of M and S, being severe and moderate. So in this case, we just are drawing one line, and we're connecting to the type of structure that we're interested in, as well as what kind of damage we're interested in. So in this particular case, we're looking at severe damage for a type 2 and type 3 structure, and that is from a 10 kiloton weapon, and it looks like if in thousands of feet, it would probably be about 500 feet away. 1,500 feet away, because it's over 1,000 but less than 2. But that's the same area, give or take a couple hundred feet, that we see moderate damage in type 2 and type 3 structures. So again, it's the same as the other table. It's just a different way to read it. Instead of trying to get things to meet into a cone, they're simple points that have the again the structure type, its number, and the damage that you're looking at, whether it be severe or moderate. And that wraps up this whole section on blast and shock. So hopefully the takeaways that you got is that the blast component of a nuclear weapon detonation is complex, and it depends very heavily on the propagation through whatever atmosphere it happens to be in. So if it's at very high altitudes, less dense air, that's going to change the way that it's going to affect things, targets either in the air or on the ground. Weapon detonations close to the ground, we see a doubling of that shock pressure in the Mach stem because of the reflection of initial waves combining with the expansion of those waves that never hit anything. So that's it for this section on the blast and pressure effects of a nuclear weapon. The next set of lessons that we're going to be looking at is what happens underground by either a surface or atmospheric burst or an underground or a contained detonation.